this aside. Yeah, I appreciate that. Okay, thank you. So I'm going to tell you a little bit about the Kervaire-Laudenbach conjecture. So it's a very simple problem. If you take a group and you take an element in the free product of that group and a cyclic group, okay? You might ask yourself, maybe we can call this G prime, okay? You made G a little bit bigger by just one element. And you consider the quotient, you quotient by the normal closure of G prime. Thank you. And I guess fundamentally, that's the fundamental question, is you add a little bit, you add one and you take one away. Can you destroy it? Okay? That's more or less the question, right? It's a question combinatorial group theory. And this is a problem from maybe 52. I didn't realize I was going to be on camera, where I'd have notes in front of me and give you numbers and precision, but it's okay.
So what's the conjecture?
The conjecture, this is really the question now. What's the conjecture? That it's non-trivial, that it's always non-trivial. Okay? So, let's think a little bit about it ourselves. Our intuition is abelian. That's really the only thing that we're really good at, is abelian stuff. And, the thing to get focused on is, maybe I should name the element. G1 t to the epsilon 1, G2 t to the epsilon 2, Gp t to the epsilon p, where each Gi an element of our group, and each epsilon I is plus or minus 1. So the thing that we might focus on is the case, is the following case. So let's let the number of t's in W be the sum of the epsilons. Okay? And the thing to focus on is, let's say it over here, we're quickly led to focus on the case where the number of t's in W is plus or minus 1. Of course, by inverting W, right, you have the same question. I mean, who cares whether you have W or W inverse over here? So might as well just focus on the case where it's just 1. Since otherwise, Since otherwise the quotient is non-trivial, since it has a finite cyclic quotient. It has a quotient to z mod, maybe we should name this exponent some, maybe let's call it m. Right? Since we can kill g itself, just quotient by g as well. Right? So if you quotient by g as well, right, then all you have is if you quotient by g as well, then you're left with t quotiented by t to the m, right? Which is, maybe I'll just write that over here. I think this is something that I can leave to you instead of fail to explain it, okay, myself. Okay, it's pretty straightforward. So the focus is really on this case of plus or minus 1. Of course, it's not actually the way that the story ends up playing. I cannot, for the life of me, believe, I'm not an expert, I cannot for the life of me believe that nobody thought about this for, say, 50 years before. I'm sure someone considered it, but maybe they didn't spell it out as a conjecture, because combinatorial group theory existed for probably 60 or 70 years before 1952, right? In some state or another, which is, I wish I could give a survey of combinatorial group theory, a history lesson. It's very interesting. There's a book by Magnus and Chandler on history of combinatorial group theory, in fact. So I'm sure someone or multiple people have thought about this, but they didn't spell it out for everybody. I know that it came up for Kervaire. It came up separately for them, I believe. It came up for Kervaire he was a topologist. It came up for him in the context of some topology thing, and the topology sorted out whatever it needed to sort out without this, and so it never got worked out by the topologists. But then it came to have a bit of a life of its own. That I'll tell you a few of the highlights. Let's first maybe generalize it before we should generalize it, and we should also mention some danger. Okay, maybe first some danger. A standard example illustrating danger. Okay. So to express that, I need to say one more thing. What people found is that maybe a sweeter conjecture in this special case is the following sort of tighter statement, which says that actually, if the number of t's in W, the exponent sum of t in W, is not equal to 0, then there's actually an embedding of g in the quotient. which is very satisfying for combinatorial group theorists. Okay, and I'll tell you a little bit about what's known over there, and then let's point out an example that we should all be aware of. Well, what if you took a word, a very simple word like this, G1 T, G2 T inverse, where G1 and G2 have a conflict with each other, where the order of G1 and the order of G2 are not equal to each other, then we're going to get into trouble when we form the quotient, because G1 and G2 are conjugate to each other in the quotient, right? This you can rewrite this as, or G1 inverse is conjugate to G2. Okay, and so when you quotient by this word, you're actually forcing G1 and G1 inverse and G2 to be conjugate to each other, so they have to have the same order in the quotient. So G would not be able to survive, right? So let's be very explicit. Maybe G1 is 1, 2, and G2 is, let's be even more aggressive. And G2 is equal to, and maybe, I tried to have, this has order 3 and that has order 2. Okay, I'm trying, and maybe G is A5. That's simple, right? And now, well, A5 together with this element T, quotiented by 1, 2, 3, 4 is conjugate to 1, 2, 3. A5 is going to get destroyed, right? So G might even be trivial in this quotient, right? Because A5 was simple. We made 2 of its elements. One had order 2, the other one had order 3. They're conjugate to each other. Their images are conjugate to each other, so their images must be trivial. So we actually kill A5, okay? So you really do need, of course, it's obvious that since the abelianization is infinite, it's obvious that you're not going to kill the whole thing. But this is somehow a more natural conjecture. You want G to survive, and if you don't have an exponent sum, if you don't have a non-zero exponent sum, you can completely destroy G. Okay. And then I'm really taking too much time over here, but let's get one more thing out of the way. How do we generalize this statement? And it became very clear how to generalize it as soon as there was some progress that I'll tell you about in a moment. Let's talk about how to generalize it ourselves, or I'll lead us to guess. Let G be a group. Let W1 through Wn be elements of the free product of G with a free group of rank n. So we will add n generators, and we're going to kill n elements. Same game. Okay, and your same abelian intuition says, okay, it's going to there's going to be something left over. You can't destroy the whole thing by destroying as much stuff as you're adding. And what's the let's focus on generalizing this conjecture, right? Although you already know how to generalize the original conjecture. Let's focus on this one. So what we do is we look at the exponent sum matrix. Let A equal the exponent sum matrix. Each entry of capital A, the matrix capital A, is the number of TIs in the word WJ. That's the natural thing to be doing. And so this becomes if the determinant, I even almost heard it in my ear, if the determinant of A is non-zero, then the quotient of G prime, then G, the natural map from G into the quotient of this free product, mod all of these words that we want to kill, the natural map is going to be an injection. Okay, and that's the conjecture. Okay, so let's go to the first progress over here, and what I think I'll do is I'll list some of the classes of groups where some progress has been made. Okay, and then I'll just tell you about the different methods that were used. It is fascinating, the variety of different ideas that have been. Yes, please.
This conjecture is as old as the original one, or is
it's it's probably they're probably older than Kervaire-Laudenbach. So I mean I don't know. We'd have to look at ChatGPT will tell us one day what really happened here. I imagine it came up immediately after the first positive contribution towards Kervaire-Laudenbach, which I'm about to tell you. Okay. However, I've seen this one referred to as Howey's conjecture, who was a second important contribution towards Kervaire-Laudenbach. So I don't know for sure. I think it's fair to say it was a pretty it was pretty straightforward conjecture after what I'm about to tell you. Okay, so let's.
Much later than Howey was in the 70s.
What Howey's contribution that I'll tell you about was 1982. Okay, so let's. So let me tell you some. Let me list some stuff that was done here. The really first Gerstenhaber Rothaus. Okay, I might be missing an H. I have met both of these guys in their 80s. One at Penn. You met Gerstenhaber, sure. Yeah, and Rothaus at Cornell. They proved the following. They proved that that the conjecture, in fact, both forms. I'll just write. That let's call this one star. You know what? How about that? If G is finite, okay, and I think it's a good idea to mention now that maybe we should just remark it over here. If if you know that if you know that well, I guess let's call it like that. So it's really hence if G is residually finite. And that's worth actually stopping and thinking about that for a moment. So what does residually finite means? Residually finite means every non-trivial element of G survives in some finite quotient of G. Okay? So if you've not seen this type of thing before, the infinite cyclic group is residually finite because any non-zero number is non-zero mod some sufficiently large n. Okay? Now, it's pretty easy to see that if you it's pretty easy to see that that the statement of this conjecture really only depends on finitely generated subgroups of G, first of all, right? Because there's only really a finitely generated information over here. So if you could prove that if you were interested in a particular group G and you wanted to know that no matter what W you choose, as long as you'll always have something non-trivial, it's actually enough to prove it for finitely generated subgroups of G. So if you knew this for finitely generated groups, you would know it for all groups. Okay, and it's also fairly easy to see that if the conjecture is true for all groups in a certain class, then it's also true for any group which is residually in that class. In particular, if you could prove it for all finite groups, then it's true for any residually finite group. Okay, these are pretty easy. It really is pretty easy to do that. So yes?
I mean, in the pro-finite case, don't you have to modify that conjecture somehow? I mean,
that's interesting. I didn't realize you're a pro-finite person.
okay.
They're out there. There's you might be interested in talking to Mark Schusterman, who I asked him about this, and he immediately lit up on pro-finite stuff, and had his own version of things. Yeah, that's an interesting game. I am a residually finite person, but not a pro-finite person, strangely enough. Okay, and I understand that it's, and I sympathize that you have to change the statements, which is kind of fascinating. I continue. Let's go to the next contribution towards this. This is, I think, 1962. They actually, their proof, maybe I'll sketch it soon, their proof used compact Lie groups. A gem, in fact. I'll probably sketch the proof in a bit. Next contribution is Howie. '82. You told me in the '70s, which is probably when he did it, in the late '70s. But I remember '82 because it's convenient because it's '62. Huh? That's right. So he proved the following. He proved that it's true if G is locally indicable. What does that mean? That means that every finitely generated subgroup, every non-trivial finally generated subgroup of G has an infinite cyclic quotient. Right? So in the this type of group theory world, locally means every finally generated subgroup has a property. What property? Indices, right? So you get an infinite cyclic quotient. And this is if you haven't seen it before, this turns out to be a very natural class of groups. For those of us coming more from geometry topology, irreducible three manifolds with boundary, compact three manifolds with boundary, their fundamental groups are locally indicable. So I'll just maybe populate it. Let's say knot groups. Fundamental groups of knot complements are locally indicable, or one related groups if they don't have torsion. I'll just write one related groups. I mean, by one related group I mean a group with one relator, right? Assuming that the relator is not a proper power. These are also locally indicable. Okay, so there are natural examples out there of locally indicable groups. And how we prove this conjecture for locally indicable groups, his method was towers. He used towers. Towers and the Adams lemma. So Adams got his name lowercase. Sorry.
It's a lemma.
Okay. I don't know how those rules. I don't know the rules, but I'm okay. You're saying. Thank you. So, so what are towers? Maybe I'll put it over here. Oh, stick it over here. So a tower map is a composition of covering maps and subcomplexes. So you start with a complex. Maybe the complex is X, and you take a cover of it, and then maybe we'll call this X1 and X1 hat, and X2. This is a subcomplex of X1 hat, and then you take a cover of that, and so on, until you get to the top of the tower, Xn, maybe. And you might restrict yourself to the type of towers. So the type of tower would usually be, what type of covering map are you allowing yourself over here? Right? Now it's an arbitrary tower. Excuse me?
What kind of complex is it?
Two complexes, in fact. There are two complexes here. And tower maps of two complexes. And in fact, the type of covers that he uses are infinite cyclic covers. So I'll just say cyclic, but I mean infinite cyclic. Towers actually, for people who might have seen this towers before, they come from three-manifold topology, where they were used by Papakyriakopoulos to resolve to give correct proofs of theorems proven or asserted by Max Dane, the loop theorem, the sphere theorem, the disk theorem, etc. Okay, and Papakyriakopoulos used Z2 towers. So Papakyriakopoulos, that's where they first showed up. I'll just write Z2 just so you can see what I mean. So double covers. Okay. In fact, there's a very, very fascinating analogy between three manifolds and one-related groups, and towers also show up in one-related group theory, which is surely why Howie was involved in this, because he's an important figure explaining, giving clear explanations of what one-related group theory is about, using infinite cyclic towers, and we're sort of hidden inside of Magnus's early one-related understanding of one-related group theory, which was his PhD thesis about one-related groups. His supervisor being Max Dane. Okay, so towers appeared first in one-related group theory behind the scenes, and then explicitly in Papakyriakopoulos. Okay, so the Adams lemma is a very interesting lemma about that when you have a two complex with trivial homology, with trivial second homology, and you take an infinite cyclic covering map of it, then the cover also has trivial second homology. It's a beautiful lemma. I said I would give a sketch of this. Maybe I might end up not doing. I'm being a little slow. We'll see. Perhaps I'll mention Klyachko now.
People over there can't have a lot of audience.
I am donating my chair to one person, and you could just bring in another. Bring one more chair over here. I'll come and get it. It'll be very embarrassing, and then just come in, and then we won't have to deal with that. Yeah, just come on in. You're better off over there than outside. For the camera, there are 400 more people out in the hallway, but the fire inspector came and said we can't let them all in. Okay, so I still can't use it, right?
No.
Huh? It's still, yeah, but at least we got them in. So, let's sketch Gerstenhaber Rothaus. Why not? Let's do that first. Huh?
I can see it fine.
Zach, you can't see it, right? Okay, so Gerstenhaber, so here's a sketch of Gerstenhaber Rothaus. They do the following beautiful thing. They take G and they say, well, our finite group G embeds in a closed-oriented, compact, I said closed, Lie group. Okay, connected is important. Okay, otherwise, well, it was already zero-dimensional Lie group, you people. So how's that? I guess I would take a group and put it in a finite symmetric group, and then then you put it in an orthogonal group, but that's maybe not good enough, so you do SU, N, or whatever it is. Okay. So, and then you do the following thing. This is a closed, orientable, connected Lie group. You make a function f from this Lie group to itself, which is given by f of m equals W of M. That's confusing. So my word W, let's, I have it over there, right? So W is G1 t to the epsilon 1, G2 t to the epsilon 2 dot dot dot, G p t to the epsilon p. Well, you just plug M in for the t, right? And so your word is just a formula, right? A formula involving multiplication and inversion. So it's a nice continuous map from this, gives you a nice continuous map F from the Lie group to itself, right? That takes each element to plug it in. And well, since it's connected, F is actually homotopic to F prime, which is equal to t to the number of t's in W, which ends up just being t. How so? So for each I, right, so this is the identity map from M to M, right? F of t equals t, F of M equals M, okay? For each I, let sigma I be a path from the coefficient gi to the identity element of M, be a path in M. Okay, and this is the first honest homotopy that I've ever done in my life. Usually, I just say do this, and you say yeah, you could see. But here, there's an actual formula. If you could find the path, we said it's connected, so it's path connected, right? So what you're doing is you're deforming this function f from M to M. You're slowly varying each of its coefficients till they become identity elements, right? And when they become identity elements, you just have f prime is t to the epsilon 1, identity t to the epsilon 2, identity dot 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 t to the epsilon p. So it's just it just becomes t if for instance your exponent sum is 1. And then the degree of f ends up being the same thing as the degree of f prime, which is 1, right? So we're looking at the degree. So we're imagining, how it treats the highest homology, and then there's a differential topology calculation. I guess this was one as well. Let's wave our hands though and say that there's some computation that differential topologists can do for us, and they tell us, well, since the degree is non-zero, that forces f to be surjective. Okay, and then so that we know that the degree is 1, since it's the same as the degree of f prime. If it having degree 1, it's forced to be surjective. Therefore, f of s is equal to the identity for some element s in our closed Lie group. Okay, but that means that we've kind of found a solution to the equation, and that's a theme that comes up over here. So let's make a little diagram that shows us what's going on. G is embedding in M, and it maps to, okay, I wrote it out. Here's G prime. And we found a way of mapping T to M, right? We send T to the element little s, and when we send T to little s, I'll just write that over here, T maps to S, that induces a map from, well, W gets mapped to the identity, so it induces a map from W maps to the identity when T maps to S. So there's an induced map from the quotient that we're interested in to M. So let me, maybe I'll write it like this. Okay, so we have our homomorphism from G to M extends to a homomorphism from the free product G prime to M, which sends W to the identity. And so we see that G has to embed in this quotient because the composition is an embedding. Okay? This is their incredible, beautiful, amazing proof. It's somehow, it's not a simple proof. It's a proof that takes advantage of powerful, fundamental tools that were available. And it looks so perfect that it just looks like it was made, it was built that way, but you know, they discovered the proof. I didn't show you what this other proof looks like. There's something interesting over here. There's a disk diagram involved, and then after that, you take a disk diagram and you look at maximal tower lifts, and you do homology computation, and you reach some type of contradiction over here. I want to tell you about a third approach. Klyachko. '92, why not? And Klyachko proved that G, that Klyachko proved, I guess his first version. He only proved the one variable case. I'll say star is true, namely G embeds in G prime mod W. When G is torsion free, meaning every element, every non-trivial element has infinite cyclic order, right? I guess another way of saying that is that subgroups generated by one element are indicable. That's a horrible way of saying that, what torsion free is. But it's, how do you feel? What is more general? Certainly, if you're locally indicable, you're certainly going to be torsion free. Torsion free is quite a bit more general than locally indicable, in fact. How do you guys feel about torsion free versus residually finite, which is more general? Mathematicians don't like to, I'm the only one that likes to answer those types of questions. The real mathematicians don't like that, those types of questions. Makes them feel uncomfortable. But I like, that makes me feel comfortable. What do you think?
With the pro-P case, it's like ZP would be torsion-free, but not really.
So you gave a profinite answer to that question. Huh? Interesting.
So yeah, just
Yeah, no, now I know more about you. So I like that. I guess that it's an interesting business. I think torsion-free is probably more common than residually finite. But I mean, you're comparing two uncountable classes, right? So, so it's more common for in practice for humans, right? I think torsion-free comes up a little more often, but who knows?
may produce torsion.
That's your argument of yeah. Okay, that's I like to argue about these types of things, but I want to tell you more. So, Klyachko's argument, which actually has not been generalized to the multivariable case, okay, uses his famous car lemma. Now, of course, if you call something a car lemma, that means it must be very, very clever. Huh? Tesla. Okay. No politics, I was told. They told me no politics. So what is his car lemma? So his car lemma is the following. You take a map of the world. Okay, there's politics already because I have borders over here for the countries, and so there's a big country all the way on the outside, and you put a little car going. Klyachko taught me to say anti-clockwise instead of counterclockwise. Makes much more sense. So there's a car traveling inside of each country counterclockwise. And his car lemma says that the car lemma asserts that there must be at least two total collision points. Okay, so let's say a little bit more. This is serious. The cars have to keep going around and around, so they have to progress infinitely. They can't just like sort of slow down and never continue. They have to go and make progress and go infinitely often around the circle. Also, if you reverse time. Okay? And what is a total collision point? Well, how many cars can be at a point? Well, most of the points are just inside of edges, right? So mostly a total collision point will be when two cars are traveling along the same edge and they crash into each other right in the middle of that edge, right? But another type of total collision might be where you have several cars that might come together and crash into each other at the same vertex, and boom, they crash into each other all at the same time. So all the cars that could be there are there at the same time. That's the collision point. Okay? And you can sort of, I know what you're doing. You're imagining a flow right over here for this situation, and you see that if you try to escape the total collision, you'll end up with an edge collision, right? Okay. The number 2, what do you think it is? It's on the sphere. we've tiled the sphere, so it's the Euler characteristic. Yeah, it is. And Klyachko pitched his Carr lemma as appropriate for a, mathematics Olympiad competition, right? I failed. I didn't get a gold medal when I tried to do it myself. Okay. He ingeniously managed to, how we use disk diagrams, of course. So there are disk diagrams over here, which is certainly any combinatorial group theorist faced with this question would naturally want to use disk diagrams, which is what we've trained to think of, in terms of disk diagrams or measuring whether an element might represent the identity, right? If some element of G represented the identity in this quotient, then what you could do is you could find a disk diagram where the outside is maybe I should have drawn that in I'll fake it and draw some other stuff like this just to give you a sort of flavor, but without losing myself. I mean, I can go on and on about this, but I'm not going to. There'd be a disk diagram where the outside is a path or a word in G, and the inside are two cells which correspond to copies of W or W inverse. Right? So there's a whole bunch of them. I'm just moving very quickly. And so if there was a word in G that represented the identity, you'd be able to find such a disk diagram that would sort of prove that it's the identity. It's just expressing the word as a product of conjugates of relators, product of conjugates of W's and W inverses. And then what you can do is you can kind of crush all the T's. These are all T's. The black ones are T's. I made a mistake. You crush all of the G's, and you end up with a sphere because you've crushed the blue path on the outside, which is made out of G's. You end up with a sphere, and each country is one of these regions. And then Klyachko found ingeniously, right? He even focused on a special case that I'm not mentioning over here. He had to do a lot of crazy things. He managed to show that if there was an element of G that died in the kernel, you'd be able to choose such a disk diagram that was a witness to that, and you'd be able to create a traffic pattern, as he calls it, which demonstrates that there's a flow of cars with at most one collision point. Okay, and he, it looks like I don't think he's a salesperson, Klyachko, but someone might have set this all up to make themselves look good, and he looked good. It was brilliant. It's a brilliant proof. Klyachko actually, went into a slight period of hibernation after that, and then, he's since emerged and has done many other beautiful theorems about Kervaire conjectures. A lot of work. I have about 6 minutes left. I'll mention that I'll neglect the authors. André Tom made a lot of contributions over here using some algebraic topology, and also there's a proof very popular in Israel. Sophic groups are popular over here. You even have to be Israeli to know why they're called Sophic groups. So there are proofs in that situation as well. I've been interested in this for a while, making very little progress towards it. But I'm fascinated by the diversity of the attempts at proving it. It's very, very interesting. And I ask my students, I've asked them, what do you think? Is this evidence that it's false or evidence that it's true? And I think it's evidence that it's false to have the diversity, many different proofs without a universal proof, because there should only really be one good proof of something. And Frédéric Paulin corrected me and said, no, it's just evidence that it's interesting, right? And I thought about it a little bit more. I think that it's evidence really just that it's a very, the question is a very general question. It doesn't have a lot of extra baggage in it. It's just a very, very simple, pure group theory question, which can take a different shape in different fields with different. If you have a different attitude on it, you can dress it up in the way you want to and approach it the way you want to, and it has its own meaning over there. Okay, so I think that's probably correct. Although I think that the conjecture is true, and I also think that the diversity is evidence against. I'll tell you one. I skipped stuff. I apologize. There's many other people have made some nice, beautiful contributions over here. I'll tell you in 4 minutes about one other small contribution. With the, I probably won't be able to spell it out. My co-author Andy, who's a quite brilliant algebraic geometry student at the University of Toronto, but was an undergraduate at McGill when we started talking about things related here. And we showed that the conjecture is true in the star-star form when G is a subgroup of, let me write a very special case like this, is a subgroup of the units of the ring of power series, the Magnus ring, if you haven't seen it. If you have. So this is the ring of power series in some variables. You can assume that the variables commute or that they don't commute. It's the same proof works. This is the Magnus ring of power series. So these are just stuff like x plus xy plus 3x squared y squared plus dot dot dot. Okay, and it's an easy game to play and see that such a power series, as long as the constant term is plus or minus 1 over here, as long as it's a unit in the coefficients, it's invertible. Okay, with what you think. It showed up with Magnus realizing that he could embed. So Magnus invented these when he realized that he can embed a free group, say a free group of rank 2. He embedded it into the units using the map that sends x to 1 minus x and y to 1 minus y. And of course, you know x inverse is 1 plus x squared plus x cubed, et cetera, et cetera. Okay. So this is what happens to you as a combinatorial group theorist if you were daydreaming during calculus, okay, and you were really interested in algebra instead. So I ran out of time. I'll just tell you what our method is. Banach fixed point theorem. So we took a map from this from an ideal in this ring to itself, and we showed the map was contracting. The map is of course related to the word right? So we used W to create a map from the ideal generated by the variables to itself, and it's a contracting map. So there was a fixed point, and that fixed point gave us a solution to the problem. And so, in some sense, we're again finding a solution to the equation inside of a certain context, right? Our theorem is interesting for being worse by far than anything anybody's done in the topic, because all such groups in this group of units are residually finite, torsion-free, locally indicable, et cetera, But interestingly, another paradigm, another connection to, the real world and the natural, the sort of superhighways in math. Will this shed light on the topic? Nah, probably not. I doubt it, but we'll see. So thank you for listening to me.